Imagine you're running a race. Every 10 seconds, you glance at your watch. Pace, heart rate, distance, just checking in. Except every time you look, you lose a fraction of a second. You break stride. You finish third. Would you have finished first if you never looked down? Maybe. The act of measuring changed the way you ran. That's not just a running problem. It's the root of some seriously strange physics, and it turns out it's a software problem too. To see something, you have to interact with it. Light is made of photons, tiny particles, each carrying a little bit of energy and momentum. When they hit something, they bounce off, and some of them bounce into my eye. That's vision. That interaction, that bounce, is so small relative to you that it doesn't do anything. You don't feel the photons. You're not disturbed by being looked at. You're just enormous compared to them. But that same disturbance doesn't stay irrelevant forever. It scales with what you're measuring. Take a car tire. In order to check the pressure, we have to let a little bit of air into the gauge. But it doesn't matter. The tire's got so much air in it that a little puff is nothing. Do the same check on a balloon. The same little puff isn't nothing anymore. You can watch it visibly deflate. Try it on a soap bubble, and the act of checking might pop it out of existence. Same interaction, wildly different consequences. Now take that idea all the way down. Past the balloon, past the soap bubble, down to a single electron. To see an electron, to find out where it is, you still have to do the same thing you did to see me. Bounce a photon off it. But here's the thing, an electron is tiny. It's not enormous compared to a photon, it's roughly the same scale. So the photon isn't a gentle bounce anymore, it's a shove. So here's the trade-off. You find out where the electron was, but the photon that told you that also shoved it, changing its trajectory in the process. You know where it was, but you've lost the ability to predict where it's going because your looking is what changed it. And this isn't just a light thing. Sometimes you measure a particle by colliding something else into it, and that collision changes it too. Sometimes you use magnetic fields or radio waves instead of visible light. But radio is still made of photons, just a different frequency. Every method of looking runs into the same wall. To observe something, you have to interact with it. There's no interaction-free way to look. This is the world of quantum mechanics, the physics of the very small, where this stuff isn't rare or exotic, it's just how things behave at that scale. It's also the seed of some things you've probably heard of. Schrodinger's cat, a thought experiment about what it even means for something to be undetermined until it's observed. Heisenberg's uncertainty principle, which asks something deeper than what we're covering today. Is that undeterminedness just a limit on how we can measure, or is it a fact about reality itself, whether or not anyone's looking? Both of those go further than the observer effect, and they've got their own episodes coming. Stay tuned. But the root of all of them starts right here. You can't observe something without disturbing it. What actually matters practically is the degree. The smaller and more precise the thing you're looking at, the more that change costs you. That's not just a quantum thing. It's a software thing too. You can't observe a running system for free. Every log line, every metric, every trace, that's an interaction. You're bouncing something off your code to find out what it's doing. And just like the photon, that interaction has costs. Now, to be clear, that's not an argument against observability. Observability has real value here, you need it. This is an argument for being deliberate about it, because it's not free, and it's worth understanding where that cost lands. Sometimes it's structural. Say you've got one clean expression, takes an input, returns a result, no visible steps in between. If you want to look at how long a part of it took, or which condition inside it actually fired, you can't measure that from the outside. You have to break the one expression into several steps, so there's something to attach measurements to. The functionality hasn't changed, the shape has. Sometimes it's overhead, and that's sneakier, because it hides inside something that looks free. Wrap a timer around a function that takes 10 milliseconds and the timer's own overhead is a rounding error. Wrap that same timer around a function that takes 10 microseconds and the timer might cost more than the thing you're timing. At that point, you're not measuring the function anymore. You're mostly measuring the timer. And here's where scale comes back. Add a metric to some giant service. A monolith with 100 endpoints, years of history. Nobody's quite sure what half of it is doing anymore. The system still feels it, just like the tire that loses a little air. But relative to everything else already going on in there, that one metric barely registers. It disappears into the noise. Now add the same metric to something small, something tight. A little pure function, 11 lines long, doing exactly one job beautifully. That's not a tire anymore. That's the soap bubble. In the monolith, that one metric was one small thing lost among thousands of other things happening at once. Here, there's nothing else happening. The metric isn't a small addition to a big picture. It's a meaningful fraction of the whole picture. That is the observer effect showing up in your codebase. Break the expression apart to see inside it, and you've traded shape for visibility. That's the structural cost. Wrap it in a timer, and depending on how small the function is, you might end up measuring the timer more than the function. That's the overhead cost. Either way, you can know exactly how long something took, or you can keep it exactly as clean and fast as it was. Same trade-off as the electron, position or trajectory. You don't get to have both for free. So, what do we actually do with this? Well, first, expect the cost to be biggest exactly where you're proudest. Your tightest, cleanest, most elegant code is the code most vulnerable to instrumentation. That's not irony, that's the physics. It's small, so the disturbance is relatively large. Second, budget for it. Observability isn't a free side effect of just adding a log line. It's a feature with a cost like any other feature. Decide on purpose what's worth knowing instead of saying yes to every request because each individual one sounds small. Third, when you need deep visibility into something small and precise, consider whether that visibility belongs somewhere else. Sometimes the answer isn't instrument the tiny function, it's observe it from one layer up where the measurement is a tire, not a soap bubble. None of this means don't measure your systems. It means know what measuring costs, know where it costs the most, and know where that cost is worth paying. The moment you instrument your system to understand what it's doing, you've already changed what it's doing. And the smaller and more precise the thing you're looking at, the more that's true. That is the observability paradox. If you've got a story about a beautiful piece of code that observability slowly ruined, or a bug that only exists when nobody's watching, tell me about it in the comments. I want to hear the worst ones. And remember, physics is awesome, software is human. See you next time.